told that a number is divisible by 2 if the unit digit is divisible by 2, divisible by 3 if the sum of the digits is divisible by 3, divisible by 11 if the alternating sum is divisible by 11. So certain weighted sum divisible by D, meaning certain weighted sum is divisible by D. So what was available in the literature at that time was that how do you take that, how do you know that you have to take sum of the digits or alternating sums? So how do you check those weights? So those weights are that what was known was that k, k square, k cube, and so on, that's taken as a weight. But what is k? K is congruent to 10 modulo D. So if your D is large, k remains as 10. So there is no simplification in the divisibility test. So what he proved as a kid was that k can be taken as an inverse of 10 mod D, provided D is co-prime to 10. There are other things also, but this is a beautiful observation for a child that he's discovering his own formulas, that this is not working for large D, and so you can take k as an inverse of 10 modulo D. So I mean, there are more results in that paper, but this is one instance which I'm sharing. So Khare's PhD is in representation. However, when he moved to Stanford, he was introduced to a rich interdisciplinary culture. I also learned from one of his interviews that this interdisciplinary culture was his wife's suggestion. So that's good. So today, I also saw one of the Khare's book, which teaches mathematics concepts for the real world. Beautiful. The title of the book is Beautiful, Simple, Exact, Crazy. Mathematics in the Real World. So I will read a preface of the book. I'm sorry, I'm taking time, but because he has so much, I cannot, say everything, but that will take one lecture for me, but I will just read the preface. It's interesting. Apurva Khare and Anna Lachoska, his co-author, explain the mathematics essential for understanding and appreciating our quantitative world. They show with examples that mathematics is a key tool in the creation and appreciation of art, music, literature, not just science and technology. The book covers basic mathematical concepts from logarithm to statistics. They also explain how modular arithmetic helps keep our online transactions safe, how logarithms justify the 12-tone scale commonly used in music, and how transmissions by deep science probes are similar to knights serving as messengers for the traveling prince. Khare and Lachiska Enlightening Mathematics Tour will appeal to a wide audience. So it's a general book which seems very interesting, but I just saw it today, so I'll definitely go through. I would like to go through it. So he has much more to his credit, and he has collaborations with field medalists like Terence Tao that reflects the potential he has. And so I would request students, if you want to know more about him, please visit his Wikipedia page. And also do see his interview with Apurva Khare published in the Hindu. It's available online. And also go through 75 under 50 scientists shaping India. He's one of the scientists listed there, published by DST, Government of India. So with these words, I think we have our today's speaker before you. So may I request Professor Arun Grover to chair the session.
Good evening, all. So let me just share with you that initiation of Sarvadaman Chawla lectures is my gratitude to the mathematicians of Punjab University in shaping my role as a Vice Chancellor of this university. I was a student here. There's a Bhamba, there's a R.C. Paul, P.N. Mehra, G.P. Sharma. They were the four stalwart scientists on the campus, and we were very overwrought by them. 20 years down the line, Professor Bhamba inducted me as a professor of physics, and I spent 3 years in the physics department. Another 20 years down the line, I arrived to serve as a VC of Punjab University, and Professor Bhamba was a member of the Senate, and mathematician Professor Bhandari was the registrar of the university. And actually, my appointment letter was signed. So when I came here, I was close to these mathematicians, and in the very first year, an honoris causa degree was given to Professor Raghunath. And I had learnt about Professor Chawla from Professor Raghunathan's lecture given to a general audience in Bombay, where he talked about mathematician. Purely after Ramanujam and Harishchandra, Chawla was described. So I talked to Professor Bandari, and very next year, 2014, I had met Manjul Bhargav several times in Bombay because he come here. Manjul was awarded the Fields Medal in 2014 in the ICM held at Seoul. I think Ma'am Raka had gone there. She was at UI at that time. So the university was run by the physicist VC with the help of two mathematicians based rather than UI or both. Anyway, so next year we thought of awarding the honoris causa degree to Manjul. Manjul accepted, and as soon as he accepted that, it occurred to us that we were felicitating Professor Bhamba in his 90th year. So we thought it's the right occasion to initiate a Sarvadaman Chawla lectures, annual Sarvadaman Chawla lectures on behalf of mathematics, and let the first lecture be given by Manjul. Manjul immediately agreed, and Professor Pasri was there at that time. So this is how we started those lectures. Another 2 years down the line, the Senate decided to award honoris causa degree to Professor Bhamba. So in that year, this new building had come up in the Sector 25, International Students Hostel. And since the Wikipedia describes Chawla as a British-born American mathematician of Indian origin, so we thought we must get this all put up. And Professor Bandari wrote a beautiful write-up on Chawla, and that is what has been put up in the International Students Hostel, Sector 25. So we have all heard how great Chawla was, how great her students and mathematics department had stalwarts right from the beginning. Gopal Singh Chawla was there, then Sarvadaman Chawla, parallel to it was Professor Gupta. Building is named after him. So he was a student of his father, as well as he worked with Chawla and then later on to Bhamba, and a whole lot of other very celebrated mathematicians who used to walk around when we were students in the Punjab University. And still there are very eminent mathematicians in the mathematics department. So the mathematics students must feel very proud and must feel very motivated that you have such a rich heritage. So thank you, Apurva, for agreeing to give this talk. I met him in the annual meeting of the academy. And I was very fascinated to listen to him. I went to him and said, would you come to the university and give the Sarvadaman Chawla lecture? It was given by Manjul and Sujata and so on. Within very immediately. So I'm grateful to mathematics colleagues who followed it up. And here we have him here. He's not only giving a lecture here, he's giving 2 lectures on the National Mathematics Day, which commemorates Ramanujan's birthday. And Apurva was a part of that Olympiad movement, and every year the Olympiad medalists are honored in Homi Bhabha Center for Science Education by holding a seminar and having these expository lectures for them. And we used to do it in December, but at some stage Raghunathan said, no, we must do it on Ramanujan's birthday. So that is how we started to honor these Olympiad medalists on the Ramanujan. Few years down the line, Raghunathan got National Mathematics Day declared on the December 22nd. So this in brief is the history of our National Mathematics Day. I had got an endowment from Sudha Murthy ji at one time, which used to give the cash awards to all these Olympiad medalists. So that process continues even today. It was started in the year 2002. We are in 21 years it has gone on. So some traditions are good to initiate, and celebrated people honor them, and that is how they become legends. I hope now that I am a retired person living near to the university, I hope to keep coming to the annual Sarvadaman Chawla lecture every year. Thank you very much.
Alex.
ओ माइक्रोफोन नहीं, माइक्रोफोन तो ऑन है जी। चलो स्टार्ट स्टार्ट Okay, I think I can start. So first of all, thank you very much to the department for inviting me here, and Professor Grover and everyone. Yeah, it was first of all a truly kind introduction, and I'm very honored to be here in the department with a lot of rich history, giving this lecture with a lot of rich history. It's on a personal note, I was very happy to come here because it allowed me to meet somebody whose paper I have been citing for the last 10 years, Professor Vasudeva. I was supposed to meet him 6.5 years ago, but 6 years ago, I think, but it didn't work out. So, यहाँ आना हुआ तो उनसे मिलना भी हो गया. So I'm very happy about that personally. And I'm sure my collaborators, we all keep citing him, will also be happy. Anyway, but it's a great pleasure to be here in Chandigarh. It might even be my first time in Chandigarh, and definitely at Punjab University. And I hope this is not the last time. So I'll start. So I'll want to talk today about a problem that actually, if you look at the list of people who are the collaborators in this problem, two of them have, one of them already has given a Chawla lecture, and one of them is Terence Tao, but that's not the one who gave the Chawla lecture. But Terence Tao has been studying the Chawla conjecture, which was not mentioned among the results of Chawla, but the Chawla conjecture has been studied by number theorists, including Terence Tao, for quite a long time as well. Okay, so the title of the talk is Polymath 14. I'll describe a little bit about the Polymath project and so on. Sorry, yeah, so I think we started at 5:35 or something, let's say, I'll assume that. Okay, and from word games to an analysis definition of abelian groups. So we all have seen, the first thing one sees after joining a maths BSc program is what is a group, what is an abelian group, things like that. And then you keep seeing groups either in algebra or maybe you later on go to see Lie groups. Lie groups are manifolds and you see them in geometry, or topological groups and so on, right? So topology, yes, geometry, yes, algebra, yes, and analysis, I'm not sure how much until you go to harmonic analysis, but then again, that is Lie groups. Or at least that's, I don't know much about that. So the idea behind this talk is to tell you a very simple question whose answer turned out to yield a definition of abelian groups using analysis. And so, good. So let me start more broadly. So, mathematics is part of the broader sciences, and the polymath project, the polymath philosophy is the idea of crowdsourcing a mathematics paper or a mathematics problem. Get lots of people to simultaneously attack a math problem. Now, this is not very common in math, but certainly it's common all over the other sciences. In biology, I mean, I'm giving you sort of the most spectacular successes of these sciences, not everyone, but the Human Genome Project, which obviously got much recognition, in addition to being very, very fundamental, has on the paper where it appeared in Nature, there are 200 plus authors. I'm just wondering if I should remove the chair. Is it visible, the bottom of the screen?
Yes.
Okay, take it. Otherwise, I can remove the chairs. So there are 200 plus authors, and some of those authors are actual institutions. So really, lots of people worked on something like this. Okay. Let's see. So the Higgs boson in physics, again, this is the paper where they announced it, it seems, and there are, I don't know, 3,000 plus authors. There's many labs, many people over many years were involved in this. The Atlas collaboration alone probably has a ton of human beings, authors involved. From the small scale to the large scale in physics, gravitational waves is very recent, another spectacular discovery. And this one, I had to go to the archive to see the paper in PRL. 100 plus institutions are named on the archive and 800 plus authors. So really very, very highly crowdsourced projects in the sciences. What about us? So mathematics, of course, has lagged behind and still lags behind in spite of this COVID thing, enabling Zoom and things like that. We largely still are one person or two people or maybe three people if you're lucky doing research, sitting in your own lab. So, of course, Ramanujan's name is mentioned. Ramanujan was sitting in obscurity in South India, working on his own until he wrote to Hardy, and then he got called there. But even earlier, Newton, Fermat, all these people were working in isolation. But forget, those were very old times when communication was slow. But even in the day of the internet, Andrew Wiles worked alone to prove Fermat's last theorem until he worked with one more person. And then in this century, Perelman worked alone to prove these big conjectures to get $1 million and the Fields Medal, which he turned down. Yitang Zhang worked by himself to prove the twin primes, to bring it down from infinity to what, 70 million or something, right? And that is by and large the model in mathematics. Researchers work alone or maybe with a student or some people, 3 or 4 people to solve a problem. Now the polymath project is something which is slightly different in philosophy. Escape. Okay. Yeah. Okay. So I will. What I want to tell you. Escape the video. Feedback. Alt tab. Yeah, so today I want to talk about the polymath project, which is a slightly different mechanism, and yeah, it is crowdsourced. Eventually, there are 6 people listed on the paper, but there are many others who helped in small ways, who are not listed on the paper, but really it was a community effort to solve this problem. Okay, oops, so yeah, so the start of the picture is about groups. This is a question about groups. So again, groups show up all over the sciences as symmetry objects. Right? So groups of symmetries. Whenever we talk about symmetries, essentially that's the same as groups. For example, you can look at, so this is I think a water molecule and ethane molecule, C2H6, and each of them has some symmetries. rotations, reflections. In math, you can talk about rotations of the plane. In physics, you have things like the Lorentz group. पार्टिसिपेंट्स को म्यूट करना पड़ेगा सबको, आप देख सकते कौन कौन पार्टिसिपेंट्स उसको नहीं इस पे प्रेस करो, हाँ या इस पे प्रेस करो, याद है सब पार्टिसिपेंट्स ये नो नो हाँ कहाँ कहाँ there are some technical. Is it possible to get the list of participants? Somebody in the participant list might be unmuted. That is the experience. I don't know. It's not mine. It's not mine. It's a charger. I'll continue. Okay, sorry. So let me continue then. Yeah, so we are going to talk about groups. And you see groups as showing up in physics, in biology or chemistry, maybe I should say. In biology, people talk about eigenvectors of a matrix, it seems. I have not encountered these, but yeah, that's a group. If you think about the entire space of vectors as a group under translating method, push or push, things like that. Permutations of a set in math, you talk about take a set of 52 cards and you shuffle them. That's a permutation of 1 through 52. And that's the set of all these shufflings form a group. And the point is, so what is really a group? Sorry, am I not? Okay. So the idea is you can think of a group as a set of, so there is some physical system or some abstract system, I guess. You look at a bunch of different symmetries of that system. Like if you think of a circle or but circle marked with these points or something, you can rotate. Each symmetry, what it does, it fixes the entire system as a whole. It takes the system to itself, but it can change the individual constituents of the system, right? So that's what permutations do, if you will. And so given two such symmetries or elements of the group, one can either compose them. You first rotate by 20 degrees, then you rotate by 30 more degrees. That's composing two rotations. You get a rotation by 50. You can reverse them. You rotate by 20 degrees clockwise, you can rotate it counterclockwise, and you reverse the symmetry. And of course, if you rotate and if you do both of these operations, you take rotation by 20 degrees and then unrotate by 20 degrees, then you get back the original system untouched, right? So that's called the identity symmetry. It basically is a symmetry that does nothing, keeps every point to itself. Right? And that's what a group is. A group is a bunch of, you can think of just the set of symmetries. A group is a collection of these symmetry objects. You can compose, you can reverse, and there is one very special symmetry called the identity in the group. And then do all composing of symmetries gives the same answer, meaning if I do one thing and then another or another and then the first one, the answer is no. For example, you can think of these matrices, which are 2 by 2 matrices, determinant is not 0. They're invertible matrices. What are these the symmetries of? Well, 2 by 2 matrices act on the plane, on vectors with 2 coordinates. And so, and you can act by every matrix on a vector and get a new vector. You can undo this by acting by the inverse of the matrix. If you multiply general 2 invertible matrices in the opposite order, you don't get the same answer, right? So here the 1 is above, here the 1 is below. The -1 and the 1 have switched positions. So a group is said to be abelian, of course, if all pairs of symmetries satisfy that you can compose them in either order and you get the same answer. Right? So I'm sure for most people here it's very basic. way more basic than it should be. But yeah, that's what an abelian group is. You don't see a full stop here because I'm going to write this down differently, which is that you can also talk about composing with the inverses. And so if you compose these 4 elements, if I put alpha inverse on both sides, the alpha inverse cancels. I get alpha inverse equals beta. And now I can further compose with beta inverse, and then the beta cancels, and I just get the identities. So this is the same as that statement. And this quantity in the red is going to be very important. That's the commutator. Okay, so that's one thing. That was groups, and the other ingredient, maybe I should say this, right? So I'll write this down here. So alpha beta equals beta alpha. This commutator is what I care about. This will keep showing up again and again. Okay, so the norm of a vector again is, well, we know what it is. It's the distance, is the length of the vector. It's the distance from the origin, right? And it's all, there are some obvious properties. This length is always positive, except the length of the 0 vector is 0. If you take a vector, and you have done this in high school, you double the length, you double the vector, then you double the length. You triple the vector, you triple the length. So there's the scaling of length, and this is true as many times. You add it up 5 times or n times, you multiply the length by n. Fine. So now let me define a norm on a group. So now that is something that is not, well, was not done, I guess, or something. It's the same idea, but is it really useful or not? What is an application of this? So this talk is an application of this definition. So a norm on a group is exactly the same idea. It's a function that takes every element of the symmetries, every symmetry, to a real number. And what are the things it must satisfy? The norm or the length of any symmetry is positive, except if that symmetry is the identity symmetry. The identity symmetry is special, it has 0 length. Every other symmetry has positive length. Okay? If you have 2 symmetries and you compose them, then it's like adding up 2 things of 2 sides of a triangle. So the red vector plus the blue vector equals the black vector, and the length is less than the sum of the 2 lengths. That's the triangle inequality. And finally, the scaling property. Now, because I'm talking in the plane, what is the composition law for vectors? It's adding 2 vectors. In a group, it's just we write down a circle or a dot. So I'm saying if you compose an element with itself, a symmetry with itself n times, I want the norm to be a norm. So it should be n times the length or the n times the norm of the original alpha symmetry. This should be true for every integer. Okay. So what is an example of such a norm? Well, this is an example of such a norm. The group of vectors under addition is a group. What is the inverse of a vector? It's exactly the negative. So if you go northeast by 1 unit and then go southwest by 1 unit, you undo exactly that. So that's the negative, right? And you come back to the same point. So that's a group under addition, and this has the usual length function, and it is abelian, meaning whether you go right then up or up then right, you get to the same point. So regardless of how you add 2 vectors, that's like drawing a parallelogram, right? You go on either side of the diagonal, you get to the same point. And this is also what one calls torsion free. Torsion free just means that, yeah, that there is no element, there is no vector which is non-zero, and you multiply it by some 5 or 10 or any non-zero number, and you still get a 0 vector. Right? So what is an example of torsion? Well, think of the clock, and if you rotate by 90 degrees, that is torsion, because, well, you can rotate 4 times and come back to the identity symmetry. So torsion-free symmetry or torsion-free element is something which is A, not the identity, and B, no positive or negative power of that is the identity. Okay. So in fact, one can show that every abelian and torsion-free group has a norm. Okay. I will actually do this. So I'm going to obviously get technical very soon, and then I will actually give you a proof of this. Right? Okay. So the question that I had was, one can show that every abelian and torsion-free group has a norm. I will show you this in one slide. The question that I had around 2014 was, does there exist a non-abelian group with a norm? Yeah. So, so by the way, so first of all, let me just tell you why, if this condition is true or if this condition is true, right? The group, if any group has a norm, it must be torsion-free. The torsion-free part is easy. Good. So, but okay, let me still tell you. Yeah, why? Just so everyone can follow this. So, if I have, say, if I have one element whose, say, which is not the identity, but its 4th power is the identity, right? Now, suppose that element is not, so it's not the identity. So its norm is positive by the first property. Now, its fourth power, the norm is 4 times the power by the third property. And the fourth power is the identity. So its norm is 0. So 4 times the norm is 4 times the original norm is 0. But the original norm was positive because it was non-zero. How can that be possible? Right? So this cannot be possible. So the only element which is torsion in a group with a norm is the identity because of the third condition. Okay, so the torsion free part is easy. If a group has a norm, it is torsion free. But does it have to be abelian? Or can there be a non-abelian group with a norm? This is a very, very basic question. There is nothing assumed about the group. There is nothing about, is it a Lie group or is it some compact group or what is it? Any group which we learn in the first day of algebra. Can there exist a group which is not abelian, but with a norm, with a length function? Okay, so then so as I said, I came to this question in, I thought 2014, but maybe 2015, because of some work that I had done with Bala Rajaratnam in probability. And then starting from April, then I started asking lots of people, in lots of different countries and in the US in lots of different universities. And somehow there was no answer that was given. Nobody could give me an example of a non-abelian group with a norm. And nobody gave me a theorem that said that such a group can never exist. Okay, so what is the answer? Now let me start getting more technical. So non-abelian groups with metrics. So metrics is everything without the norm part. Okay, so without the last condition. So non-abelian groups in metrics occur in geometry. So there are things like called word metrics in free groups and monoids. There are things on the Lie group itself. On every Lie group, there is a left invariant Riemannian metric. And on compact Lie groups, there are things called bi-invariant metrics, meaning you pre-multiply by the same element. That doesn't change the distance between them. So like this one, the distance of A times G to A times H, you multiply by A on both sides, on both terms. It doesn't change the distance. Okay? And you post multiply by B, and that also doesn't change the distance. So that's left invariant and right invariant. So these kind of things do exist. It's just the question of, are they norms or not? Is that scaling property there? The distance from the identity element to 5 times to G power 5 is 5 times the distance from identity to G. So let me, in the language of geometry, let me write down the same thing that I told you, a norm on a group. Well, let's start with a pre-norm, a metric on a group is the following. It's a length function. In geometry, it's called a length function. In analysis, you would call it a metric, in the language of Rudin and other people. So a length function on a group or a monoid is something which is the following. First of all, length of G times H is less than length of G plus less than length of H. Let me just write that for you. So basically, think of the length function as the following. The length of an element. So what is the length of a vector? As we said, it's the distance of the tip of the vector to the origin, from where you always point the vector. So by the same analogy, this is the distance in the group from the identity symmetry to that element. And so if I suppose I know that my length function is left invariant, then what is the length of G times H? So this is equal to the distance from identity to GH. And we know that this is by the triangle inequality. This is less than the distance from identity to G plus distance from G to GH. This is just the triangle inequality. But now G to GH is G times E to G times H. And I can use my left invariance condition that's at the beginning. This is equal to distance from identity to G plus distance of identity to H, because I cancelled the G from the left. And this is equal to length of G plus length of H. So we started from this term here and said it's less equals by the triangle inequality in this term, if the metric was left invariant. So that's exactly what we are sort of saying here. So a length function is a function such that the length of G satisfies the triangle inequality. The length of G is always positive unless G is the identity. Again, that is satisfied by this, right? If you have a metric on any group, then this number is always positive except when this is equal to the identity symmetry. So that's the second statement. And the length of G is equal to length of G inverse is sort of saying that distance E to G and distance G to E are the same. So really that's what it's saying here. So length functions are in one-to-one correspondence, you can show, with left invariant metrics. Length can... Exactly. Why so? The length of identity equals length of identity inverse, which is also 0. Identity is its own inverse. Both sides are 0. Yeah. Yeah. So this is the way to go from any distance which is left invariant to the length function. And the other way to go from a length function to a distance is given here. So it's actually a bijection. And these two maps are, you can check, they're inverse to each other. Fine. So this is basically it's saying the same concept, but in the language of geometry, right? In the language the geometers like. Now, what was a norm property? The norm property was if you double the length, double the vector, you get double of the length. Meaning if you write down distance of e to g power n, you get n times the distance. In the language of length functions, that would mean the length of g power n is n times the length function. That's what's written on the board. And I can take negative powers, I can take positive powers because the length of g is the length of g inverse. So I can take length of g power minus 5. That's 5 times the length of g inverse, which is 5 times the length of g. Things like that. So this is the non-abelian version of a norm written in the language of geometry. So the question really is, can the length be homogeneous? Meaning, does it satisfy this condition? If the group is not abelian, can there exist a single group which is not abelian but has a homogeneous length function? There are lots and lots of groups which have a length function, as we said. Free groups, word metrics, Lie groups, Riemannian metrics, and so on. These examples here. But homogeneity is what the question is. That's the key property. Can there exist a homogeneous metric with a norm? Okay, so there's a result of Milner, which I may or may not get to for whatever interest of time, but which says that there are certain examples, there are certain classes of non-abelian groups where a length function cannot exist. That was known before. This is one such example. This is some famous paper of John Milner, who was a very distinguished mathematician. About 50 years back, the paper was written. If G is any connected Lie group and not abelian, then such a norm does not exist. If G is of nilpotence degree 2, I'm going to skip the technical calculation here, but if G is a nilpotent group of order 2, meaning G, the commutator of G with itself is not abelian, but its commutator is identity. Sorry, the commutator of G with itself is abelian, but not identity, and the second order commutator is the identity. Then such a norm cannot exist. Okay? But there were two examples of classes of non-abelian groups where this cannot happen. But you can also talk about slightly more primitive structure. So think of the following. A group is like all the integers, okay, all the counting numbers and their negatives, because for every number you have the negative, which will be the reverse symmetry. Move by 5, go back by 5. Monoids are things which are just the non-negative integers. There's no concept of subtraction. There's just additions. 0, 1, 2, 3 is a monoid. And if you have a free monoid, meaning a monoid with no extra relations, then such a norm always exists. So as I said, I was asking lots of people, and this person I knew from my PhD days. He was younger than me, and then he was a faculty at Courant Institute in New York. So I was visiting New York, and I met him, and then I talked about the problem. So he said, I don't know the answer for groups, but I do know the answer for monoids, and this is always true. But here are two classes of groups where it's never true. Here's a full class of monoids for which always true. So, but what is it for arbitrary groups? In general, monoids are harder because you have less structure. You can't invert elements, but groups are nice. What is the answer for general groups? And does such a non-abelian group even exist? Or can one prove a theorem that says it never exists? Okay? And so now let me tell you the main theorem of the talk. Okay? So yeah, so given the any group with no restrictions about the group, the following are equivalent. So I'm going to tell you 3 or 4 conditions. The first one is algebra, which is G is abelian and torsion free. If and only if it's a metric space, G is a group. We start with G a group. It's a metric space that admits a norm, meaning a metric that's left invariant and right invariant, which further satisfies the norm property. So I'm writing the property in terms of the metric. Distance from e to g power n is n times the distance. Okay. From geometry, now in the language of length functions, G admits a length function which is homogeneous. But I don't even need homogeneous. Homogeneous was the condition that the length of G power n is n times length of G for all n. And I'm saying I don't need it for all n, I just need it for n equals 2. For one integer n, if I know this condition, that's good enough. I don't need it for all n. It's much less than a norm. I don't need this to be bi-invariant. Remember, the length functions were left invariant metrics. So it's enough to think of this as being left invariant, and it's enough to say this n equal to 2. So far less conditions than property 2. if and only if G is basically like the set of vectors in a plane. It's just the set of, it's a subgroup of a Banach. So you can say it's a subgroup of Rn, or it's a subgroup of Hilbert space, or it's a subgroup of a Banach space under addition. That's all. It's just, maybe it's a lattice in R2. The set of integer coordinate points in R2 is a group with a norm. The set of any additive subgroup inside a Banach space is a norm, which is a group with a norm under addition. You just take the norm inside your Banach space and restrict it to your group. The point is there are no others, nothing else. These are the only ones that are norms, groups with norms. So in some sense, this is like a slogan for the unity of mathematics. Because if you like algebra, well, then here is a metric space characterization of abelian groups. This is so, and if you like, if you like geometry, well, here is a functional analysis characterization of abelian groups with norms, or of groups admitting homogeneous length functions. So they are all really one and the same. And there is a quote here by Hermann Weyl that may be relevant. He said at some point, in these days, the angel of topology and the devil of abstract algebra, he really did not like abstract algebra, fight for the soul of every individual discipline of mathematics. But in some cases, angels and devils, angels and demons are one and the same. So if and only if, and it connects an algebraic property to an analysis property, to a geometric condition to just literally being a subgroup of a Banach space under addition. Okay. So in the rest of the talk, let's see how much time I have. I'll do some things. So clearly, if G embeds additively in a Banach space, then it is abelian and it is torsion free. If it and then of course, obviously, Banach space addition is commutative. So the norm is translation invariant, and it satisfies the scaling property because it's a norm in the Banach space, and that, as I said, already implies bi-invariant implies left invariant. Homogeneity implies two homogeneity. So 2 implies 3. So in the rest of the talk, let me get really technical and get to the proofs. The rest of the talk is about proving this result. I won't prove the last part of it, but I'll try to tell you some other things. Right? So first of all, let me tell you that I said every group which is abelian and torsion free can be embedded in the Banach space, and therefore it has a norm. Let me prove that for you using Zorn's lemma. And even that proof uses analysis and algebra. It combines two things again. It has to. I mean, it's abelian and torsion free to Banach space. Then I'm going to tell you why 2 homogeneity implies n homogeneity. So if I just know this condition for n equals 2, then I know it for every n. That's another small step of the proof. So I want to give you some snapshots of the proof along the way. But really, and along the way, I want to tell you about this polymath project business. Remember, I started by saying polymath, so I should tell you about the polymath project. And finally, the highly non-trivial assertion is why, if it satisfies these conditions, is it abelian? Torsion free is easy, as we said. Why is it abelian? Okay. So let's start with 4 implies 1. So abelian torsion free groups embed into Banach spaces. Okay. So why? So suppose G is abelian and torsion free, then it's what one calls a divisible abelian group. It's a divisible group in some sense. Well, okay, not quite. Okay, fine. So what you can do is you can take tensor products. You first take the tensor product. It's an abelian group, so it's a Z module over the integers. Take the tensor product with R. Now, in general, that's an enormous space. So, for example, if your group was the real line, it's an abelian group. If you take the tensor product of the real line with R over Z, it's huge. It's uncountable dimensional. It's really, really. If you took the tensor product over R, you get R. But if you take tensor over Z, you get an enormous. Right? So, but it's a real vector space because the G had torsion free. And G is embedding inside that, and then yeah. Now, the point is, the key is by Zorn's lemma, every real vector space has a norm. How do you do that? Well, take a basis, take a Hamel basis, take any vector space basis, give each of those basis vectors norm 1, and take the L1 norm with respect to this basis. If I take summation Ci vector Vi, and each Vi is a basis element, you give Vi the norm 1, and you say summation Ci Vi is norm summation mod Ci. That's the L1 norm. That's a norm. So take this enormous, potentially enormous vector space, give it a norm, and look at now this smaller space, G tensor Q over Z. So what does tensoring with rational numbers over integers do? It just says I can take denominators. All it does is introduce 1 over n's every time. And now suddenly you see this becomes much smaller. If G was to the real line, this is enormous. But this is just saying I can put denominators in my real numbers. I just get real numbers. So this is suddenly down to the real line again. So you bring it down much smaller. The key point is you had to go all the way up there to introduce a norm. Once you have a norm, you can restrict to any additive subgroup. Just the norm remains the norm. And it is a norm under integer multiples. So that's fine. So this is a Q vector space now, our rationals. And you got a norm for free using the axiom of choice. You restrict that norm to here. Okay. And now it's very simple. Right? When you have a Q vector space, you want to get a complete Banach space, you just take the Cauchy completion. And then you can define the obvious things that you would think of. And this becomes R vector space again. And you get the Cauchy complete Banach space. And again, so if I remember, if I start with the real line, this is enormous. This comes back to R, and R is Cauchy complete. So I don't do anything more here. So I go back to R. So this construction not only tells you that an abelian torsion-free group embeds in the Banach space, it tells you the smallest Banach space in which to embed it. If G is abelian and torsion-free, it has to contain denominators. Any Banach space containing it has to contain denominators. It's an R vector space. And any Banach space containing it has to be complete. So this much has to be part of it. So this is really the smallest up to isomorphism, smallest Banach space containing any abelian and torsion-free group. So it is actually more strong than what we needed. Okay, fine. So this is one. So as I said, I'm trying to give you actual proofs in this talk for why this. So this is why an abelian and torsion-free group is exactly the same as a G embedding additively in the Banach space. So 1 and 4 are actually equivalent. And now we get to the whole business of why does a norm imply abelian? That's really where we are going. Modulo the small detour into why 2 homogeneity implies n homogeneity. Okay. Are there any, should I ask for questions? Or is that usually afterwards? I don't know how it's done. Afterwards, okay, fine. Okay. So now again, to say 3 implies 2, meaning again, see the title, it means if I know this condition for n equals 2, then I know it for all n. So, okay, since there are students here, this is where I can ask students. Let's suppose I know that the length of G square is twice length of G. Can you tell me one other integer n for which you know this then? Yeah, 4. Perfect. Let's why 4? Yeah, sorry. So I shouldn't be, apparently I'm not supposed to ask questions or get questions, but I'm asking questions. Hopefully asking questions is allowed during the talk. Yeah, so all I do is if I take length of G power 4, G power 4 is G square square. So the length of G4 is twice length of G square, and that is twice length of G. So I can do all powers of 2 this way. The question is, how can I do all the other powers? The powers that are not powers of 2, right? So length of G power 6. And this is a very cute trick. What you do is, this is a trick from some 1970s paper that I found. I mean, probably this can be asked to like math Olympiad kids or something like that, but or even in college as exercise. But somebody actually wrote this trick down in the paper. A length of G6, what you do is, you take a power of 2 larger than 6, 8, let's say 8. Okay? And now you write down this chain of inequality. So you start from 8 times the length of G, which by the norm property, I know is the length of G power 8, because 8 is a power of 2. By the triangle inequality that's less than, you write down G power 8. So you break it down in clever ways. G power 8 is 6 powers, 1 power, 1 power. So you want the 6 power. So length of G power 6 plus length G plus length G. And now the power of 6, you break it into individual atoms. So you get 6 times the length of G plus length of G plus length of G. And so you start and end with the same term. So of course, everything in between is an equality, which means this second inequality here is an equality. Cancel the 2 factors, you get equality that you want. So this is how you prove that it's 6 homogeneous if it is 2 homogeneous. And you can keep going for positive m, and because the length is equal to length of G inverse, you can do this for negative m. So yeah. So that's the small detour of why 2 homogeneous. If I know this for n equals 2 or n equals 3 or any single positive integer larger than 1, then I will know it for all integers. That's this. Nothing special about 2. Okay. But the proof is not complete. 3 implies 2 is not complete because this wasn't the only condition. We also had the point that in the third condition, the metric was a length function, meaning left invariant. In the second point, it was a metric which was bi-invariant. So how do we get, now we know that it's a theorem. So how do we get right invariance as well? Okay? And the right invariance of the metric, when you translate it under that dictionary between length functions and metrics, the right invariance of the metric translates into a conjugation invariance of the length function. So why is this length function conjugate invariance? The answer turns out to be 2 lines or 3 lines long, but it was a very clever piece of math, which I later on was sort of almost ashamed I didn't think of it when I learned the answer. So we will get there. Okay. So now torsion free was easy. Norm implies torsion free we talked about. So the really non-trivial implication then, modulo that right invariance, is that G has to be abelian. Torsion free is fine. Let me skip this slide. Fine. This is this Milner business. I'm glad to tell you afterwards. But yeah, so as I said, I had this question for a long time. I emailed lots of people. I met Robert Young, who said that for monoids, it's always true. And now we know that for non-abelian groups, it's never true. So it's completely opposite. But what was the answer in general? I didn't know. So I was working on this problem in matrix positivity and entry-wise functions, which I was doing. And I had a long paper with Terry Tao in August 2017. But then in 4 months later, in around exactly this time of the year, we had the winter break at ISC. My teaching was over. So I had some grant money. I went to meet Tao again, maybe to take that project forward. But in passing, I mentioned this problem. And then he got very interested in this problem. So we just ended up discussing this problem. Is there a group with a norm? And here is what we discussed. So suppose G is any group with a norm. Again, I will use the language of the symmetry elements from the beginning. Take two symmetries or take two elements alpha, beta. The key quantity, which I call KQ, to understand is the norm of this commutator. So now this fellow shows up again, and this fellow shows up throughout the talk. Now, the length of the commutator. Why is this the key quantity? Because if this key quantity is 0 for all symmetry, all pairs of symmetries, then when is this 0? When is the length 0? The length is 0 if and only if the element is identity. When is the commutator the identity? If and only if the group is abelian. If alpha and beta commute. So if I can show that this key quantity is 0 for every alpha and beta in a group with a norm, then I have abelian. That's what we want. Easier said than done. How do you show it's 0? So of course, again, being an algebraist, I might have thought, you somehow show some exact identities. And being an analyst, Tao said, no, the correct way to do is show it's less than epsilon for every epsilon. So this is and here G is any group. So I can't assume any kind of fancy things like, Silo theorems, which anyway can't be applied because it's an infinite group. But Lie group, Lie theory, I can't assume anything. It's an arbitrary group. Because you have only basic tools to play with. Where just the definitions almost. Yeah? And you have the norm property. The norm property is what makes all the difference, obviously. There are plenty of Lie groups with metrics, even bi-invariant metrics, but norms aren't there. So the norm property is what matters. And so can one show that it's less than epsilon? And this is also therefore the first talk after, like the first problem or the only problem I've worked on, I think, where I really learned to love the Archimedean property of real numbers. I mean, you see this is the first day of analysis class. Real numbers satisfy the Archimedean property. For every, every positive real number, there is an n such that 1 over n is less than that. So this is the talk, this is the problem where I really learned to appreciate that property, because that is the one property that gets you out of jail in some such situation. So, okay. So you want to show that this key quantity is 0, meaning it's less than epsilon for every positive scale. This is not the use of the Archimedean property. That will get. Okay, so first of all, let us normalize it. So, okay, I just care about, let me fix 2 elements. The idea is fix any 2 elements in my group with a norm and just work with those elements, their inverses, and just words in those 4 letters. So basically, it's enough to say, I look at the subgroup generated by alpha and beta. If the bigger group had a norm, I can restrict it to the subgroup. That also has a norm. So I can just look at a non-abelian, if you will, subgroup generated by 2 elements and only work in that subgroup with the norm. So that's what we did. So you want to show this thing. So there are 4 generators. First of all, you can rescale a norm and you still always get a norm. If you divide the norm by 2, it's a norm. If you multiply a norm by 5, it's a norm. So rescale so that all the divided by large enough number so that all the 4 lengths are less than 1. Okay. From this now, can you tell me, so basically, can you tell me one bound on this thing, the length of this element? One upper bound. The length of this element is at most something. 4. Because of the triangle inequality, if all the individual letters are less than 1, then you get 4. Now let me tell you that its length, I can bring down that 4 to 2. I remember, I want to bring it down to 0. I want to say less than every epsilon. Right now we have epsilon equals 4 is trivial, just by the length. You can do 2 in the following way. It's preserved under conjugation is what I'm going to say. That is the right invariance of the metric. is the same as conjugation invariance of the length. If you believe this for now, I will prove it on the next slide. Then I claim that this can be bounded above by 2. And it's basically written here with, if you see, if this is a black dot, you can see, then that's the 2 elements here. Or I split it differently here, but yeah, it's length of a product of a string of 4 letters. You take out the first one, you keep the others are a conjugate. So that length is the same as length of alpha inverse, but those were both less than 1. So if you believe that the length coming from a norm is conjugation invariant, then the length is less than 2. But you can do slightly better. How can you, I'm going to improve this to 4 over 3. All this was part of the discussion with Tao. Actually, the 4 over 3 I knew even before that. So I went to him with 4 over 3. How does one improve to 4 over 3? So how do you show that a number is less than 4/3? That's the same as saying 3 times the number is less than 4. What is the number? The number is the length of this thing. What is 3 times the number? It is the length of this thing cubed, exactly. And that is the length of 12 letters. So you start with a 12-letter string. And now you use the fact that multiplication is associative. So this is where I learned to appreciate associativity. And you really have to play with the basic notions because there is nothing more sophisticated you can use. So this is how product of 4 elements at a time is the same as product of 3 elements at a time of the same string. And now you see these are all 4 conjugates. So by the triangle inequality, it's less than the first length, second length, third length, fourth length, each of which being a conjugate, 1 plus 1 plus 1 plus 1. So you have to come up with cleverer and cleverer tricks to bring down the length from 4 to 2 to 4/3. And you want to keep going to 0. So you can imagine what kind of crazy, complex, clever tricks people would have tried. But yeah, so this is associative. So that's a good property to have in a group. Now, can we keep going all the way to 0? And this is where we stopped working. I had to go back and catch my flight back to India. Well, back to San Francisco. And then there's this long 17-hour flight of Air India to Delhi. Okay, but so this is where we stopped. And then I think that night or something, Tao asked me, can I put this on my blog? Because I can't think of anything more either, but maybe people can. So I said, sure, please do. And this is the blog post, so bi-invariant metrics. He posted it on the free group, but whatever the point was, that was because he said, if we can do it in the hardest case, where there are no extra relations to play with either, no tools, no relations, just the free group. There are 4 generators. Then we can do it on other cases. So he asked the question, and then he said that, this looks like a problem that might be receptive to a crowdsourced attack, which is the whole point of polymath. At this point, it was not a polymath project. It was a blog post. So I'm posing it here if anybody wants to work on it. And then so this he posted, and then I took off for Delhi. And then by the time I landed, I checked my email, and the whole thing had gone crazy. Lots and lots of comments and activity, proposed approaches, and so on. Okay, so I'll tell you the timeline in terms of India time. So yeah, this was night in UCLA. So, and he posted the comment with the calculations I told you, 4 and 2 and 4/3. Within 2 hours or 3 hours, apparently, one of the collaborators in the paper eventually proved that a non-property implies the conjugation invariance. So that last missing link there, the conjugate invariance, was also done. How? And the proof is going to be, as I said, something like this much. So how? This is the statement. If G is a homogeneous length function, it comes from a norm, then the length function is conjugation invariant. And one can write down the proof of that dictionary translation, but not important. So this addresses the loose end. That one loose end we had is now done. Why is this true? So proof. And the proof is very clever, of course, but then, once you see it, it's like, okay, why didn't I think of this kind of thing? Which is what I was like, why didn't I think of this for 2 years? But anyway, so the idea is the following. Take a conjugate and multiply it by a large integer, n times the length of a conjugate. Now we know what that is. It's the length of the power of the conjugate. It's a norm. We know how to take powers of conjugates. That's again the second thing one sees in an algebra class, probably. Conjugates and then how to take powers. Right? Or you just get G times h power n times G inverse. Fine. By the triangle inequality, this is less than the length of G, the length of G inverse, plus n times the length of h, because h power n. So the length of n times this thing is less than this other quantity. Divide both sides by n. What do you get? Length of G at G inverse, length of the conjugate, is less than length of h. The n cancels, plus 1 over n times some extra error part. But now this is where Archimedean property shows up, right? When you take n go to infinity, this part doesn't matter. Limit stays correct. And so you get length of h is bigger than length of any conjugate. Conjugation is a symmetry relation. So you get bigger equals and you are done. So this is how it works. So it's a very clever idea. It fits in 3 lines and it straight away gives you that the length is homogeneous, but it does much more than that. Okay. This conjugation invariance is going to be used now in extremely, well, you'll see. It's going to be used in even more intricate way. So, okay, back to the timeline. So, as I said, this is the Polymath project. There is one more interesting feature about the project. Not only was it entirely done on the blog, the whole thing is solved on the blog. It also involved sort of, nowadays you hear these things are proof checking and automated theorem proving. That's one of the instances that happened in this project. So it sort of involves a lot of crowdsourcing, happened on the blog, had computer assistance. So what happened is after this thing, the next 2 days were sort of useless in the final run of things. People were attempting to find such a group and it didn't work. So then after those 2 days, people said, okay, now let's come back and start to bring that constant down to 0, upper bound down to 0. So we had 4 and 2 and 4/3. Let's bring that down to 0. So then somebody came up with some ridiculously clever idea to make it 5/4, which is a small improvement. This is, as you see, 2 days and a little more, 12 hours later. 1 hour after that, all these are in nighttime in India. It was day in the US and Canada and so on. 19 over 16, so really small improvements, but they're really fighting very hard, to all these clever tricks and conjugates and so on. And then finally, doing lots more effort after 7 more hours. So as you can tell, this was very active blog at that point, Tao's blog for this post, because the problem is so simple. You don't need to know any Fourier analysis or like cuspidal representations or some Donaldson-Gromov invariants or something. You just it's a group with a norm. You can't use anything. So lots of people tried their hand at it, and finally it went down to below 1. Fine, okay, it goes down to below 1. I don't even know these calculations. I'm scared to look at them. So there's some crazy clever calculations. But then there was a 24-hour barrier. At this point, lots of people were trying things, making success, getting success. But at this point, for 24 hours, nothing, no more progress. And this is where the breakthrough came, sort of, I like to say that when human intuition broke down, a computer was the one that provided the next step. And that was done by my colleague, Siddharth Gadgil, and his computer. So Siddharth Gadgil actually is, first of all, so he's majorly nowadays into his automated theorem proving and using Lean to formalize the proofs and so on. But he's also, obviously, he knows quite a lot of geometry. So around this time, when he saw the blog post here, he said, I will start at that point to do both things. At the same time, I will search for examples. And at the same time, I'll program a computer to bring the constant down to 0. So I'm both believing it's true and believing it's false. And he assumed that, and he went ahead with both, very seriously. So unfortunately, this didn't work out. And now we know why, because there doesn't exist such a group. But he was continually programming his computer to do word searches. And there are 4 directions, right? You can write down words in whatever letters, 4 letters: alpha, beta, alpha inverse, beta inverse. So when you write down words in these 4 letters, then this is like drawing the Cayley graph or something like that of the free group on 2 generators. He programmed something like, the computer ended up doing, he told me, 2 power 1000 queries. Like, he really went ahead and did 2 power 1000 many searches for coming up with the proof. Finally, it came up with a proof. It yielded, okay, there is one, so if you have seen this Avengers Endgame or Infinity War, Dr. Strange says there's one future out of 65,000 billion futures in which we win. So that's the one the computer came up with. It stopped and he said, okay, I have a proof. So Endgame can happen here also in real life. Okay, so here is this proof. So you see there's almost a 24-hour gap. And so first let me read out the blog post on Tao's blog. So Siddharth Gadgil said, one can get a bound on the commutator. The earlier bound was 0.95. Then one can get it to 0.816 with a brutal proof, not optimized or streamlined in any way. The computer generated proof, which I have formatted, so you can read it if you want, is available at this URL. This is the URL. And so you see here, it says the computer writes down the proof like we as an undergraduate would have known what is a proof is a finite sequence of steps. Every step follows from the axioms, the hypotheses, and the previous steps in a logical manner. And at the end is the final. That is what we understand as a proof. So the computer spelled out every step of the calculation. So it starts with the first line is, if you can't read it, the length of alpha inverse is less than 1. Therefore, the length of the conjugate is less than 1. The third line is the length of beta inverse is less than 1. So the fourth line is therefore the length of a conjugate is less than 1, because we knew conjugation invariance by then. So continuing so on and so forth, 125 steps later, the 125th step says the length of 68 element string, alpha, beta, alpha inverse, alpha, beta inverse, 17 times. So 68 letter string is less than, what is it, 13.859 something. Divide by 17 by the norm property, the length of the commutator is less than 0.815. So rounding up 0.816. Of course, this is not going to help us solve the problem eventually. Nobody's going to do, if this is what it takes to go from here to here, like Usain Bolt shaving off 1/10 of a second or something, then how does it get to 0? It will take some horrible calculation. So, but what happened is a fourth collaborator who gave your last Chawla lecture, Pace Nielsen, he was sitting in Utah at like, this is 9:40 p.m. UCLA time. Utah is 1 hour ahead. So he was sitting there at 9:40 p.m. his time, or 9 o'clock his time after dinner. And he saw Siddharth Gadgil's post. He went to this blog post. He read 126 lines of computer output. And he said, and he then wrote down the comments. So he understood all of it. And he said, this was beautifully done. I had some intuition. This seems to be similar. And the first 43 lines established something. So he decoded what the first 43 lines do. The next 30 lines established something, which, by the way, allows a better bound on what we already had. The last 50 lines established something else. And so we are done. This is great. And we can improve the first computation in the following way. So he not only read through all of this, he then also picked it out, picked it apart, decoded it, and understood how to improve on it. And all of this was done in 100 minutes flat. So Siddharth Gadgil's post is at 8 p.m., which is 9 o'clock at his time, Pace Nielsen's time. 9:40 p.m. is this post of Pace Nielsen explaining what it does and how to improve. So yeah, there are some incredibly clever people sitting there after dinner, checking Terry Tao's blog. I don't know. So yeah, fine. So understood by Pace Nielsen, but also improved by Pace Nielsen. Fine. And then, but once that happened, people wanted to understand why. Why is this working? What is the computer doing, or what is Pace Nielsen doing? And this was finally isolated into the following formulation. I think the precise statement was by Tao. This is what Siddharth Gadgil called the internal repetition trick. So suppose I have 4 elements in any group with a norm, homogeneous length function, such that X is conjugate to Wy and to Zw inverse. So a very technical looking condition. Then the length of X is less than the average of length of Y and Z. This looks sort of a bit technical, also a bit weird, but the whole point is it doesn't depend on W. Okay? And this is going to be very powerful, as I will show you on the next slide. Okay, we are almost at the end of the proof now. Well, as much, I won't tell you the final step in the proof, but yeah. And there's a picture in the proof. So okay, let's go to the picture in a minute. Let's write down X as conjugate to Wy. So S times Wy times S inverse. Also T times the other guy times T inverse. It's conjugate. Now do exactly what Tobias Fritz had done. Take a large power of X. But now we take 2 times the large power of X. The first n of them, I write as S times Wy times S inverse. So I get the power in the middle. And the second n, I multiply the powers of this guy. So I get that. And now don't look at the third slide. Look at the picture, which should be readable at the end as well. This is the length. This is X power 2n. The first n is the nth power of X. The second part is the nth power of X. What is the length less than by triangle inequality? It's less than the length of one S and one T inverse. The bar is inverse. And then the rest of it. But the rest of it is a conjugate. W and W bar. So I can take out the W and W bar. Now again, now it's so this S, T bar, and then the things inside W and W bar. So now I again take out a Y. I take out a Z from there. Again, I get a conjugate. Again, I can remove W and W bar. And I keep going. So I basically get everything here except all the W's and all the W bars. The W's and W bars never show up because they're all getting conjugate. This is a nested conjugation, basically. Right? So So what I get is there's one copy of S, one of S bar, one of T, one of T bar or T inverse, and n copies of Y and n copies of Z. So I get the length of x power 2n is less than n times length y, n times length z, and some error term. Now you know what to do. Divide by 2n, take n to infinity, you get the average. Right? So that's that. Now, okay, this was some technical looking condition. But why was this the condition that I'm telling you now? Because I'm going to use this condition. And what was the previous bound? The previous bound was some 0.816. Right? So we will basically shave off another 10th of a second in one slide. So yeah, so just by this, by one application of this. So remember, here what we were doing is taking n to infinity, and we were using the application that the conjugation invariance. We were using n applications of conjugation invariance in this one calculation. Each conjugation invariance is an actual Archimedean property. You take some k to infinity. So there are n applications of asymptoticness here. And one application of that is going to be using, is going to do the trick for shaving off another 10th of a second. So just for fun, I'll show you this, and then that's basically the end of the, almost the end of the talk. So I'm going to specialize now to this. Does this work? It does. So I'm going to first, I'm not going to write down the power of the commutator, but let's write down the power of two copies of the commutator. Okay. This is a 9-element string. The claim is that I can choose y, z, and w cleverly so that x is conjugate to whatever it is. Wy and z inverse w or something. Sorry, zw inverse. So by the lemma, the length of this thing is less equals 2. Why? Because it's less than the length of y plus length of z by 2. What is the length of y? Y is the conjugate of a product of two conjugates. So you can remove the conjugation, and then it's length of this plus this, which is 2. Similarly, z is 2 conjugates, so 2. So the length of this number is less equals 2, this 9-element string. Now I claim that the length of my commutator, we want key quantity, right? The key quantity was the length of the commutator. I claim this commutator is less than 8 over 11. Where did I get 8 and where did I get 11? Okay, here is where I got 8 over 11. Again, it means 11 times that is less than 8. 11 times the length of this is the length of a 44-element string. 11 times 4. Write down 44 elements. 44 elements, right? So now split them into 4 copies. The moment you split into 4 copies, there are 11 elements in each. Well, guess what? Each of those 11 elements is actually a conjugate. 11 elements. Inside the conjugate, you have exactly these kind of 9-letter strings. And each of those 9-letter strings has length 2. So 2 plus 2 plus 2 plus 2. And that gives you 8. So 8 over 11. So therefore, what we just got from one application of this trick, this internal repetition trick, is we got 8 over 11, which is 0.7272. And the previous bound was 0.816. So just that's how powerful this trick is to go lower. But what the problem is, this is still one instance, and we have to do not, you might think we have to do finitely many applications of this if we are lucky, but that's not true, because every time you reduce it to a positive number, it doesn't help, right? You have to go down to 0. So the Archimedes property says you have to go past 1 over n for every n. And every time you go finitely many times, it's not going to help. So how does one keep going lower? I won't, this is the last step. I won't tell you how, because that's a little, it takes a little more time. It's probability theory, but it's binomial probability theory. So again, nothing very sophisticated. You can use either combinatorics, binomial combinatorics, or the probability of Bernoulli and binomial distributions. But it turns out that this internal repetition trick, cleverly used, does the job. Not one time, but the trick itself has to be used n times. So the conjugation, to do the conjugation invariance, you need n applications, n goes to infinity. To do internal repetition, you need 2n of the conjugation, and 2n goes to infinity. And now to prove the lemma, you need 2n times the internal repetition trick. So it's like n, like countably, many times. So it's really one idea of sort of taking conjugates, but nesting them sort of n times n, like times. Yeah. And that does the job. The final step can be written out using either, as I said, combinatorics or probability theory. And either way, the key, what is the key underlying part of it is the following. You want to show that the length of this commutator doesn't grow too fast. So we said that it was less than, it doesn't grow too fast. So you want to somehow show, if possible, the length of this quantity to the n is less than something that grows slower than n. If it's something maybe like square root of n or cube root of n. Because if that is true, then what is this? This is the same as saying it is n times the length of the commutator. And now therefore this is something like, let's say, square root of n. Then n times something is less than square root. How can that happen unless that thing is 0? You divide by n both sides and take n to infinity. And so this side that never changes and this side goes to 0, therefore length goes to 0. That's the idea. What is the quantity that it actually grows slower than? It turns out it's square root of n. And so why is that growing slower than n? Because so there is a what should I say? There is a notion, there is a quantity which for a sum of n IID random variables grows slower than n square. And that's called the variance. If you remember some basic probability, if you have seen, the variance of a sum of n IID random variables is not quadratic. It is linear. It is n times the variance. And that for basically means the standard deviation is what is square root of n. And so that square root of n was actually the standard deviation of a binomial random variable of n sums of Bernoullis. And that basically bounds a multiple of the key quantity to the nth power or times n, divide by n, and take n to infinity. And that's how we got Z. So that's basically that. Yeah, this part I didn't tell you. Everything else was explicitly written down. So as you can see, there's like, very, very basic tools that we had to use, but there were some very clever people, and there was a computer that provided some key intuition, which then allowed us to proceed and finish the proof. And so maybe I'll just end with the timeline maybe. So yeah, so this was when somebody went below 1, and then there was a 24-hour gap. Siddharth Gadgil uncovered the next breakthrough, which is computer. And then somebody, so yeah, the application I showed you actually was worked out in the blog. Everything was worked out in the blog 4 hours later. So Pace-Nielsen 100 minutes later did something. And this is 240 minutes later. So yeah, barely in the next 2 hours, somebody worked this out. And then somebody went even to 0.666. And then Tobias Fritz, the person who initially told how to prove conjugation invariance, had the idea to write down a discrete heat equation using lengths of special elements. And that is what led 3 hours later to Tau finishing the proof. So initially Tau used something called the Chernoff bound, but then we narrowed it down to the variance and standard deviation of binomial random variables. And so, yeah, so that basically led to the, sorry, I'm going to skip this part. This is some technical stuff, but that led to the paper. And yeah, and I think that is where I should stop. Thank you again.
It was too clear.
I don't know what to ask, what people can ask, but yeah, but yeah, exactly. The power of, like so many people attacking it together, and somehow they were all over the world. So round the clock, there was always every 3 hours of progress. So it was fun
This
stuff.
was second lecture on this polymath. This lecture given by Pace-Nielsen also was on
That's a
polymath.
fair point. That's right. Pace-Nielsen talked about polymath project to do the prime number gap reduction last year.
Yeah. So normally in space, in those
Pace is common and polymath is common.
polymath is common.
So yes, and Terry-Tau is common therefore, because he was
So
involved,
Terry
of
Tau
course,
is common.
obviously.
Yeah.
Yeah.
Keep on doing more polymath things and we keep
Yeah.
on inviting.
Yeah, that's very kind of you.
Thank you very much. Thanks a lot. Thanks to audience also. Now, official vote of thanks by our chairperson. Thank you.
What is it?
I request Dr. Vasudeva to present it. And